Hey, geometry, we're going to look at the second part of section 2.5. And in this section, we are going to actually dive into proofs. We mentioned them briefly yesterday. In my class, we did anyway. And we talked about proofs, and I overly simplified it, but I did say that a proof is nothing more than a math problem where you have the given information and you have the answer, you have the conclusion. All you have to do is connect the given information to whatever the conclusion is, or whatever the answer is. And that is what a proof is. It's a little bit more complicated than that. A more formal definition of proofs is a logical argument where you use deductive reasoning. And remember, deductive reasoning means you use facts, you use known information, definitions, stuff like that. And you use those definitions, that deductive reasoning, to show that the given statement is true. And the reasons we use include definitions, properties, postulates, and theorems. And a two-column proof is probably the most common way of doing proofs. However, there are other ways that you can do proofs, but we will camp out with two-column proofs more than anything else, mostly because it's a little bit easier to organize a two-column proof. And a two-column proof has numbered statements, corresponding reasons, and it shows that argument in a logical order. So let's look at this example of a two-column proof. And you'll notice on the left, we have certain statements that we will make, starting with the given information and then finishing with the information to be proven. And those are statements based on facts that you know or conclusions that you can form from deductive reasoning. When you are planning out your proof, you will, it helps if you copy or draw the diagrams yourself. You can kind of label on them. And this is what I talk about in class as math doodling. You're just kind of doing stuff mathematically, and it helps your brain get into the right direction. The one thing you cannot do is you cannot, in a proof, use the information that they're giving us. That you cannot use, in this case, the example, the fact that angle 2 is congruent to angle 1. So whatever the prove statement is, whatever your objective is, you cannot use that in the proof itself. That's your final step. On the right side, you will list whatever logic or whatever reasoning you used to make the statements on the left side. And on the last statement, you do want to give a reason for that last statement. I know at the very beginning, the first one is angle 1 is congruent to angle 2. And we know that because they gave us that. That is the given information. And that is going to be the first reason. However, you do not write proven or prove for the last one. You have to say what it is that you did that allowed you to go from step 3 to step 4. And in this case, if we know two angles are equal, then by the definition of congruence, we can say that the two angles are congruent as well. So let's look at a few examples. Oh, I'm sorry. Before we get into examples, we will talk about the other types of proofs. There's one that is a flow chart. And you can see the flow chart right here. And it just kind of, you just draw arrows from one step to the next and to show your thought process, whatever order you thought through or logically came to a conclusion. And when you're doing a flow chart, you just write the reasons underneath whatever your statement is. So instead of having a left column of statements and a right column of reasons, you just kind of have your statements and reasons together written next to each other with arrows connecting one thought to the next. And a paragraph proof is exactly what it says here. You're just writing it all out in paragraph form. That's probably my least favorite. I probably will not be doing any paragraph proofs, but I may do a flowchart proof or a flow proof. And now we will look at some examples. So best way to learn math is to do actual examples and not just read definitions of things. And this is one that you've been doing for a long time. And we've actually done a few of these already. An algebra proof, you are given the fact that 5x plus 1 is 21, and we're trying to prove that x equals 4. You're just solving an equation, and we have the answer. And remember, when you do these, you do not want to combine multiple steps into one. You want to do one operation at a time because you're going to list whatever that operation was. So if we start with 5x plus 1 equals 21, how do I know that? Because it was given. How do I know that 5x equals 20? Well, if you subtract 1 from both sides, then you get 21 minus 1. So I use the operation of subtraction. And then how do I know that x is equal to 4? Well, to go from 5x equals 20 to x equals 4, you divided by 5. So that would be your division property of equality. And if it helps you think through what you're doing, if it helps you determine what your reasons are, then don't do this in your head. Actually write down, I'm going to subtract 1. And then you have that visual, oh, I subtracted. And then to get from 5x equals 20 to x equals 4, oh, we divided by 5. And if you actually write these steps in there, when it's an algebra proof, it does help you come up with the reasons. Number 2, this one, we are not given the left column. We have to fill in both columns. Number 1, you were given the left side and we only gave the reasons. So number 2, what am I going to start with? If I'm given this and I want to show that x does indeed equal negative 19 over 25, we always are going to start with the given information. I'm just going to copy that down. 5 times 5x plus 3 is negative 4. And I know that because it is given to me. Everybody should always get the first line of a proof. You're literally just copying down what they gave you. After that, you have to decide what you would do next. So if I'm trying to solve this equation, ultimately hoping to get x equals negative 19 over 25, I'm going to start by distributing that 5 through 5x plus 3. And so my next line is going to be 25x plus 15. How did I do that? Well, I distributed. So that's your distributive property of equality. My next step, I'm just channeling my algebra skills. I want to solve for x. Let's subtract that 15. And so negative 4 minus 15 is negative 19. And again, if you need to actually write the step in here to help you decide what property you're using, that's not supposed to be a 5, to help you decide what property you're using, write it in there. And I can see that I subtracted 15. And so that line 3, to get from step 2 to step 3, I used the subtraction property of equality. And then finally, my last step, I will divide by 25. And to get from step 3 to step 4, I divided. So your final reason is the division property of equality. Again, I'm going to stress this again. I know your top column, your top entry is given, and that's your reason we knew this. You never, ever, ever at the very end, when you have the statement to be proven, you never write proven on the right side. You always write down whatever it was you did to get from the previous step to that last step. That's your last reason. Do not write proof or proven. All right. This one, number 3, I'm not going to work this one out in detail. So I'm going to reveal the answer in just a second. If you want to work this out on your own, maybe pause the video and then see what you do, see how you do. You can do that. And here comes the answer. So if you don't want to see the answer, pause it or look away for a minute. There it is. And I'll leave that up there for just a minute so you can pause it to see the answer. And let's go on to number 4. Number 4 is a long one. And we are now getting into geometry. This is not a straight up algebra proof. And this is where it gets more complicated. So we are given in this diagram right here, we're given xy equals 42. So that's given to us. And we are trying to prove that n would equal 5. Now, here's an example of math doodling that I might do, something that helps me process the problem. I would probably come up here and I would say, okay, all of this is 42. Kind of helps me think through the problem. So now what am I going to do step by step? And we need to be very detailed and we're not going to skip anything. To prove this statement, we will start with the given. We always write down the given information. Xy equals 42. How do I know that? Because they gave it to us. Now we have to start thinking about what we would do next. And so if I'm trying to solve this, well, I see that I need to add these two pieces together and get 42. Now, algebraically, you might jump straight to 3 times n plus 4 plus 3 times n equals 42. But we need to go in baby steps, itty bitty baby steps. And we are using the segment addition postulate there. So first thing I'm going to do is actually write down symbolically that the segment xz plus the segment zy is equal to the entire segment xy. I'm going to do that first, and I want to see that. So that is, whoops, I thought I had my pen or my pointer. There we go. So that is your segment addition postulate. Then I'm going to go from this to my algebraic setup. So I now am replacing xz with its given length, which is in terms of n. I'm replacing zy with its given length, and I'm replacing the xy with 42. Well, what am I doing there? What operation is allowing me to do that? What mathematical property? Well, that is the property of substitution. That substitution, I know that xy is equal to 42, so I can substitute 42 in for the xy. I didn't formally write down xz equals 3n plus 4. You could have if you wanted to, but it's pretty much given in the diagram. So the fact that that's in the diagram, I can just substitute the 3n plus 4 for the xz. Similarly, I can substitute 3 in for the zy. Once you get to this point, now in this problem, we now have nothing but algebra, and it should get significantly easier because we can go back to our comfortable algebra and equation solving skills. And so now that I have this, if I'm solving for n, and they tell us the n is 5, but we can't use that yet. We're ultimately hoping to get 5. If I'm going to solve for n, I'm going to distribute that 3 first. So 3 times n plus 4 is 3n plus 12, and that was the distributive property of equality. Then think algebra. What am I going to do next? What's my next step? Well, on the left side of the equation, I see a 3n and a 3n. Well, I'm going to combine those. 6n plus 12. I left the right side alone, and on that left side, I combined like terms. And in my class, we talked about abbreviating some things. So combined like terms, we will just call it CLT. Next step, if I'm solving for n, I want to move that 12 over, and we will move that 12 over by subtracting. 42 minus 12 is 30. And that is your subtraction property of equality. And then we have one step left. 6n equals 30. I need to divide by the 6, and I will end up with n equals 5, which is what I was shooting for. That's my objective. And that was done by the division property of equality. And so if you remember way back at the beginning, I said an overly simplified description of proofs. You're given a problem, you're given a situation, and you're given the answer. You just have to very detailed, in a detailed way, explain how you went from what was given to what the final answer is. Good? Good. Next one, I am not going to work this one out in detail either. So if you want to try number 5, you can pause number 5. And the answer is about to show up right now. And there this one is. So we can give you proofs in several different formats. The most difficult ones are going to be the ones that are completely blank and you fill in both columns. Sometimes we will give you everything in the left column and you fill in the reasons on the right side. In this case, you can see that we kind of mixed it up. And so these do tend to be a little bit easier because I tell you what to, at least half of each line. So I'm going to go on to 6. Again, I'm not going to work this one out in detail. It's very similar to the one we did just a minute ago. So here's our given information, and I'm about to show you the answer. There's the answer for this one. Here's the answer for this one. Good, bad. All right, I'm going to move on. Number 7. E is the midpoint of DF, and we want to prove that X is equal to 3. And here again is somewhere where I can do some math doodling. And we're not only solving, we're not just solving the problem, we're proving that X is equal to 3. And remember, with a proof, we do want to go in very detailed steps, starting with the obvious. I say obvious, maybe nothing's obvious to you yet. Start by writing down the given information. E is the midpoint of DF. Okay, so now I'm thinking, if I know that E is the midpoint of DF, what can I conclude? What does that mean? And you want to go in little bitty baby steps. You want to write down every thought you have. And if E is the midpoint, then that means that this segment DE is congruent to the segment EF. That's my next statement. DE is congruent to EF. Well, how do I know that? Well, because that's what a midpoint does. That is the definition of a midpoint. It divides the segment into 2 congruent segments. Now, the next step is going to look weird to you because it's just going to seem obvious, but I'm going to make the statement that if DE is congruent to EF, then DE is equal to EF. And I'll explain why I do that in a second. That is your definition of congruence, and in this case, in the context of segments. So if the segments are congruent, then they are equal. The next step is when I finally get to what you probably would have written down first if you were just solving the equation. If E is the midpoint, these are equal. That means 6x plus 5 is 8x minus 1. And we're finally at that point, but I wanted to go through these steps because we are actually, in order to do this, we are actually substituting those lengths, those variable expressions for the segments they represent. Here is why we swapped to equality. We stressed yesterday in class a couple of times, when it comes to substitution only works if things are equal. They do not work if things are congruent. And so that's why I wanted to make the leap from congruence to equality. Also, if you look at the final answer, what we're shooting for, we're trying to prove that X is equal to 3. So somewhere along the way, I had to make a change from congruence to equality. It has to happen. One, it allows for substitution. Two, my objective goal is that x is equal to 3. So now I'm finally at this point with substitution, and here on out is all the algebra stuff. And I'm going to do something interesting here that may seem to contradict what I said earlier. I'm doing two things at once. I am going to subtract the 8x. I'm subtracting 8x from both sides. And I'm subtracting 5 from both sides. The reason I can do both of those at once, I did tell you to do every step individually, but the reason I can do both of those at once is because both of those are the same property. They're both under the umbrella of the subtraction property of equality. What you definitely do not want to do is in one step add and divide. Those are different properties of equality. So you don't want to do two properties at once. This was only one property, so I'm going to do that. Then my final step is to divide by the -2, which will give me an answer of x equals 3, which is what I wanted. Therefore, that is our final step, the division property of equality for number 7. There we go. Let's look on to number 8. This one might be one of the easiest ones because almost all of it was given to you. We only have to fill in those last 3 blanks. And one little typo here, there is a floating slash right here, at least on mine there is. So if that's on your sheet, just ignore that. It's not a division symbol. Just pretend that that slash is not there. And I'm going to go ahead and reveal the answers on this one. This is kind of similar to that segment when we did earlier, only we're doing the angle addition postulate. So this angle plus this angle equals the whole angle. And you do want to do it symbolically before you write the actual equation because we're using substitution to generate the equation. And then after that, we have our algebra steps. Combine like terms, we'll subtract the 8, divide by 9, and we have our answer. And then number 9, and this is the last one I want to look at. They tell us that angle LM, no, they don't. They tell us that ray LM bisects XLN. Well, if ray LM, and my L is kind of hidden there, if ray LM is bisecting this big angle, well, then I know that this angle will be equal to this angle. So I'm already making some steps here. I'm already thinking ahead towards the problem. And I'm just kind of thinking there, but I can't go straight to that. We have to talk in detail about how we know that those two angles would be the same. And so in our proof, let's talk about how we march our way to the ultimate goal, that x is equal to 20. And we always start with the given information. LM, ray LM is bisecting KLN. And because LM bisects the big angle, then I know that the two angles on each side of that ray would have to be congruent. How do I know that? Because that's the definition of a bisector. If something is bisected, it divides the thing it bisected into two congruent pieces. This time it's an angle. Previously, we talked about a segment bisector. Or actually it was a midpoint, which is a bisector. But so KLM is congruent to MLN, and I'm looking at what I'm shooting for. I'm always thinking about what my objective is. I'm trying to prove that x is equal to 20. Since I'm ultimately looking for x equals 20, I have to change that congruence into equality, and that is my next step. I'm going to write angle KLM is equal to angle MLN, and that's the definition of congruence. If two angles are congruent, then their measures would be equal. So that's the definition of congruent angles. Now that I have equality, I feel more comfortable using substitution. So I can see in the given diagram that KLM is 2x plus 40. MLN is 4x, which is floating way up here, but that's the angle MLN. So I'm going to replace those, and replacing those symbolic angle names with what their measure is in terms of x is the act of substitution. So that is your substitution property of equality. And here we are finally at the steps of algebra where you probably are more comfortable. I'm going to solve this by saying that 40 is equal to 2x. I am subtracting the 2x, so that's your subtraction property of equality. To solve for x, I will divide by 2. And I now know that 20 is equal to x. That is your division property of equality. However, I'm trying to prove that x is equal to 20. Where's my pen? There he is. That x is equal to 20, not that 20 is equal to x. Now, I know you're looking at that thinking, it's the same thing. But I like in proofs for my very last statement to be literally what is exactly on the paper. I want it to say x equals 20 because that's what I'm trying to prove, and I don't want to anger the gods of math. So let's go one more step. Let's flip that equation around so that it looks like what we're trying to prove. And I was able to do that. If 20 equals x, then x equals 20. I know that because that is your symmetric property of equality. So there are a few examples of proofs. Your first exposure, we're dipping our toes into the world of proofs, and we'll be here for a little bit. So hopefully that makes some sense, and we will look at more of these in class as examples.